Hi everyone, we are the G.O.O.M.B.A team and my teammates are Justin Ramos and Ryan Sands. The goal of our project was to build a robot that can travel throughout a room and map out the dimensions and location of obstacles and edges. That way, it can improve upon its navigation of that room in the future for various purposes, such as cleaning, organizing, object placement, and decoration. Additionally, civil engineers, architects, and those in construction might find it useful to automatically map out a room and go to a desired location. As shown, the approach we took to this project was incrementally building upon the design in a series of levels. We successfully created a robot that could travel in a straight line, take corrective action, access an external memory source, and display data on a graphical user interface. What we did not successfully accomplish is the memory of obstacles and the ability to accept user input to travel to a specified location. Our functional requirements were very simple. We were within our goal size of 0.25 meters squared. We used the Feather NRF board along with the Raspberry Pi. We were just above our goal weight of 2 kilograms. Our cost was about half of our goal of keeping it below $200. The total cost of the project was $171. However, many of the materials we purchased are reusable: 3 sonar sensors, an infrared cliff detection sensor, and 2 DC motors.
Here we have our block and circuit diagrams. On the left, you can see how the NRF interfaces with 3 sonar sensors for obstacle detection, the IR sensor for cliff detection, the encoders for distance measurement, the magnetometer and accelerometer for turn detection, and Bluetooth for user control. The Raspberry Pi was powered with an external battery source, and the NRF was powered by the Raspberry Pi. The motors were powered by 6 AA batteries. The NRF and Raspberry Pi communicated serially via UART with the RX and TX pins for data transfer. Here is the physical design of the G.O.O.M.B.A. We have our chassis, mounted with 2 wheels driven by brushed DC motors with soldered encoders. We drove those motors with the L298 motor driver. On the front bottom, we have our IR proximity sensor. On the front, right, and left, we have the sonar sensors in their 3D printed mounts. On the top, we have our breadboard and NRF mounted on our battery pack for the Raspberry Pi, next to the Raspberry Pi itself. Underneath the chassis, the AA batteries are connected in series.
To get the bot running, we use a state machine to grab the values of all the sensors, send the data, drive the motors, and handle events. Here you can see how we used object-oriented programming to make the state machine. This shows the event handler and the decision making to change the state of the G.O.O.M.B.A. We utilize an independent timer event to periodically send data to the Raspberry Pi to get frequent updates without changing the state. For the GUI, we use PyQt5 to display the values while simultaneously reading and sending data to and from the NRF. This requires multi-threading to run these at the same time as the GUI itself. The read thread continually loops, attempting to read a signal over UART until it receives the start signal. Once it does, it then adds all the data it receives to a list until it receives the end signal, and then passes that list into the main GUI class to be handled. When the send thread is triggered, it takes in a signal for which state to pass along to the G.O.O.M.B.A and sends it along UART. Here's the method we use to read that list of data from the read thread. This method ensures that each bit of data is interpreted properly and is sent to the proper places in the GUI. Here you can see the Bluetooth functionality that we incorporated in order to test the robot. We also have preliminary testing using all of these sensors, the Raspberry Pi, and the UART connection in order to test sensor data and drive the motors at the same time. When it comes to programming, we learned how to establish and maintain a GitHub repository for working on code remotely. We also learned how to tackle UART communication to concisely send data, and we also got some good exposure to PyQt, which is a super flexible GUI. When it comes to hardware, we found that wires can often break in the middle or cause weak connections elsewhere. If we were to iterate on this design, we would change the chassis to be bigger and more adaptable so that we can more easily attach components. We would also consolidate from 2 power sources to just 1 to conserve space. Trying to establish reliable connections between 6 AA batteries and hook them up to the motor driver was the longest and most frustrating issue we had throughout the project. As for software, we found that the sonar library affected the PWM signal to the motors based on the trigger timing. Finding an alternate library for the sonar or a different sensor would improve performance.